Okay, happy Thursday. We are Thursday, week 6. And this is the second half of our second to last chapter. So excited. Today, it doesn't say lab on here, but after we do section 9.2, we're going to do lab 5. It's going to be really fast because we're just going to use the continuous data you already have and that you've had for a while. We're just going to reuse it. So it is actually super fast. So section 9.2, we're taking stuff from 8.1 and we are expanding on it. So 8.1, we dealt with means and sampling distributions of means. So we are going to construct confidence intervals with means instead of with proportions. We did proportions on Tuesday. We're going to do means today. And we're going to learn something, a t-value. A t-value is similar to a z-score, and I will show you the difference. It's very little difference, and we'll talk about how to find those and whatnot. And then also, after we construct our confidence interval, we will work backwards and we'll look at how to find the sample size to estimate the population mean. So basically, we're doing everything we did in 9.1, but we're doing it with means instead of proportions. So it is basically the same thing. So I don't even need to re-explain what a confidence interval is because it's the same thing, it's just with means, right? So point estimate, we already have this definition. It is a value of a statistic that estimates the value of a parameter. So it's something from the sample, a characteristic of the sample to estimate that same characteristic of the population. So here we are going to be using X bar. We're going to be using X bar, which you may recall is a sample mean. And so we don't have to do a calculation like we did with p hat. We're just going to say that our mean equals our X bar. So we're going to estimate that the population mean equals our sample mean. That's all we're doing. That's what the point estimate is with means. We just say mu sub X bar equals X bar. All right. So I'm not even going to do this because you guys know how to find a population mean. So I'm just going to move on. Oh, here it is. Or a sample mean. We just take them all, add them all together, divide by how many there are. So we have that our estimate, our sample mean is 2.464. So we're estimating that our population mean is about 2.464. We generally round to 1 decimal more than our raw data, just like we've been doing the whole term. So with mean, 1 decimal further than our raw data, or whatever my open math tells you to do. And on a test, if I don't tell you, I'm not going to get mad at you for rounding for something different than my head says. But if I tell you, obviously, do what I say. Okay. So a t value is dependent on a sample size. And so this is very similar to what we did with z-score. So it's calculated the same way that we did with z-score. This right here is, this right here is the standard deviation. You guys may recall this from chapter 8. This is like the new, I'll write new. So the new standard deviation, and we take the sample mean, subtract the population mean if we have it, and then you divide by the new standard deviation. Don't worry about degrees of freedom right now. We're going to talk about degrees of freedom in a minute. The t-distribution follows n-1 degrees of freedom. Don't worry about that right now. We'll talk about that in a minute. The reason we're using the t-value, the reason we're using t-values is because our standard deviation, we're using S, we don't know the population standard deviation. Since all we have is a sample standard deviation, we are using t-values. T-values are not super different than a z-score. You're finding the distance a value is from the sample mean. That's really what you're doing. So a t value and a z value are basically the same thing. Just one of them is dependent on sample data and the other one is on an assumption of population data. That's really it. In this class, when we're dealing with means, we're going to use t values. When we're dealing with proportions, we're going to use z values. Just stick with that. I have a couple of slides at the end that compare things side by side. So hopefully it'll be helpful. Plus, there's a really good handout, I believe. All right. So this kind of helps you right here. So we're going to take a look at both the Z and the T. So you can see by looking at these that Z has population, T has sample. But I'm going to show you what happens as our sample sizes get bigger. And you will see the difference between the Z-scores and the T-scores. All right. Here's the histogram for Z. Using Z-scores, converting every data value to a Z-score, this is what it looks like. Here's a histogram for T. Notice that Z, they're all squished right there in the middle. T values, they kind of spread out a little bit more in the tails. Both tails on both sides, they kind of spread out a little bit more. Both of them are normally distributed. Both of them are bell-shaped. Just the T value is spread out more. There's more in the tail than with the Z. And a lot of that has to do with sample data. I'm not going to ask you to tell me this. I'm not going to test you on whether or not you know this or understand this. I'm just trying to explain the difference since I'm suddenly introducing something brand new like that. Okay, our histogram for Z is symmetric and bell shaped. The center of the distribution is at 0. Almost all of our rectangles are between -3 and 3. It follows the normal distribution. For the T-score, it's still symmetric about the 0, has longer tails, it's more dispersed. It still follows the standard normal distribution, but it is just more spread out in the tails. And it's because we're using samples, and because using samples, our samples will offer a wide variety of different means, and so it gives us more dispersion. It gives us a wider bell curve, and it's okay. So, but I'm not going to ask you to redo it or to explain it to me. So here's what the T distribution, it's going to be different for different degrees of freedom. In this case, in order to simplify what degrees of freedom we are, degrees of freedom, we're going to just call that sample size. It's a little bit more complex than that, but you don't need to deal with a little bit more complex. We're just going to stick with calling it sample size because you're not going to need it to be anything different. So we're centered at 0 and it's symmetric about 0. The area under the curve is 1, just like it is with Z, 50% on the left and 50% on the right. Same with Z values, as it increases without bound, gets goes towards infinity in one direction and the other, it's going to get really close to 0, but never reach it. These are the things that are basically the same, except for this. The area in the tails is a little bit bigger than it is with Z because we're using samples. So as our sample size increases, we are going to get closer and closer to the same curve that we see with our Z-scores. So it's going to get closer and closer as we get bigger sample sizes. So basically, once you get past 30, it pretty much looks like the Z distribution. So once you get a sample size that's greater than 30, it looks almost exactly like the Z. Okay, so take a look here. So the blue one here, the one that's on the top, the blue one, that is perfectly normal. So the orange one down here, which would be this one right in here, this one is with a sample size of 5. And so you notice that it is a little bit more spread out. It's a little bit lower and more spread out. And then I have a 15 sample size, and it's getting closer. It's almost to the normal. The normal, if I went to 30, you almost would not be able to tell a difference between the normal curve and the t value. All right. So we notate t as t sub alpha here. It's just like we were doing z sub alpha. We're going to be doing t sub alpha divided by 2, just like we did with z. We're just replacing the z with a t, but it's going to be the same thing. All right. So I'm going to show you what this looks like on the t table. So we're going to find a t value. So the area under the distribution to the right of the t value is 0.2 with 10 degrees of freedom. So I'm going to have this, I'm going to draw my curve. So this right here is 0.2. This is my t sub alpha. So this up here is 0.2. Oh, we're looking for the area. I just lied to you. I just lied to you. Okay, wait. So the t value is 0.2. The right of the t value. Hold on a second. Oh yeah, no, I did it correct. Okay, let's take a look. Let's just take a look. Let's go to my t table. Okay. So our t table is the same thing as this is not the t table. Go scrolling down. So on the t table, notice the t table, we are looking to the right of the t value. On the z value, z's, we are going to the left. The t table is on the back of the z table, and we're looking at the area to the right. Okay, our degrees of freedom is right here. This is our sample size. The df is the sample size right here. So we're going to go to 10 degrees of freedom, and we're looking for 0.2. So there it is right there. So our area under the curve to the right, and see, I should have paid attention because it would have been is 0.879. Oh, look. I didn't realize I had I had it right here. So take a look, 10 degrees of freedom. And we're looking right here, 0.2. This is one tail. Don't worry. We'll talk about tails in a minute. This is one tail, so it's just to the right. So 0.879. I'm going to highlight it with a different color right here. So you look at what your sample size is along that degrees of freedom column, and your area is right here. So we're looking for the value of t, so what that t value is given the area. So these kind of work backwards. You're given the area and you're looking for the t value. These work backwards of the z tables. So you're given the area, we are looking backwards. So my t value, t sub alpha, is 0.879. So we are 0.879 standard deviations above whatever that mean is. Questions? All right. So I would like you to try this if you have a Z table, a T table. If not, I will go to one. So we're looking at a T value of 0.05. You're looking at 15 degrees of freedom. I'm going to go to my T table. So if you don't have that, the area is 0.05 and you're looking at 15 degrees of freedom. So if you don't have a T table, go ahead and look at mine. So here's my 15 degrees of freedom. We're going to go 0.05 to right here, 1.753. So that T value with the right tail area of 0.05 is 1.753. Questions on finding the T values? Okay, I'm going to show you a nice, easier way to do this. That's not where I want to be. So if you're in your fancy schmancy calculator, if you do second vars, number 4 is inverse t. This is the kind of like the other inverse norm. So if it gives me an area of 0.05, which is just what we just had, with 15 degrees of freedom, hit enter, and it gives me, says negative, but it does, the inverse t gives you a left tail instead of a right tail. So you just need to make it positive. Because unfortunately, inverse t gives you a left tail. You just have to realize that the table and what we're using gives you the right tail. So you're just going to have to make it positive, or you could put 0.95 if you want.
Is there another name for it? Because I'm not finding that under second vars.
So you can't see inverse t.
Mm-mm.
And it's not number 4. What's your number 4?
Number 4 is TPDF.
Oh, I wonder if it is in the catalog.
Oh,
Let's check it out. Let's see if it's in the catalog. Don't know. Yeah, I see it right there. You might have to do it in the catalog if it's in yours. At least it,
scrolling still.
yeah, it takes a while. Could be worse. It could be something that starts with V or something.
Ugh. Nope, I don't even have it in my catalog. It goes
Okay.
inverse norm and then I part.
Okay, let's see if we can, let's see if Google is our friend. Inverse T on which calculator do you have?
TI 84 plus.
84 plus. Let's see if it'll tell me anything.
Thank
Calculating
you.
inverse student T. Okay, that doesn't help me. That doesn't help me. Okay, let's see if we can find it anywhere else. No, that's not helping me. I wonder if you just don't have, as you're probably lacking an update. Yeah, see, it says in which distribution, go to inverse T. So I'm gonna have to do a little bit, wait, see, don't have inverse T. You might just have to use your, use the, okay, yeah, but, and it's not anywhere lower on
No,
the list.
yeah, there's like keep going round and round.
Mm-hmm. Okay.
The
Yeah.
only inverse is inverse norm.
What is the
Uh,
inverse T? Yeah, I don't see it. So you might just have to use the table,
okay, thanks.
unfortunately. Yeah, I will keep looking for it, but you might just have to use the table. Thankfully, the table's not terrible. So the thing, so if you have to use the table, once you get past uh once you hit 40, then it jumps. So let's say that you needed 45. Let's say that you're right here and I needed 45. I would just split the difference. That's what I would do. Because this is 0.851, this is 0.849. I would use 0.85. So if you get higher than 40, you're going to have to be a little bit more creative, or you can round to the closest one. So let's say they gave me 42, then you're going to just use 0.851. It should not cause problems because once we get to numbers greater than 40, it's basically a Z-score. So you should be okay. All right, so let's continue on here. Okay, so when we're using a confidence interval for mean, we're doing basically the same thing. Well, first thing, it has to come from a simple random sample or randomized experiment. They need to tell you it's simple random sample. If they don't worry about it. But also you have to have your sample size needs to be less than 5% of the population and either normally distributed or a sample size greater than or equal to 30. And I'm going to write this down because I think there's a question in your homework about it. So it's either, I'm going to write it in a different color. This one's not standing out. So either normal population or n is greater than or equal to 30. So if it comes from a normal population or my sample size is greater than or equal to 30, then you can use this math. Okay, now we're going to talk about n-1 degrees of freedom. As I stated earlier, the degrees of freedom, we're going to just call that the sample size. We are going to use, when you are looking for your critical value, your T sub alpha divided by 2, when you're looking for that critical value, look for it with n-1 degrees of freedom. So if my sample size is 15, use 14 to find your T value. If your sample size is 28, use 27 for your T value. The reason that we do that is because we're dealing with sample data. It's the same thing when we were calculating the sample standard deviation. We're dealing with sample data. So there's variation in like our sample standard deviation, and there's variation there because we're dealing with samples. Therefore, we account for that variation by subtracting 1 from our sample size. So it's going to make my confidence interval just a little bit bigger. So, or just a little bit smaller, sorry. So it's going to make it just slightly different. So you need to use n-1 degrees of freedom when you're finding your critical value. I'll show you when we do the example. So just like when we were doing with proportions, you take your critical value and you multiply it by the standard deviation. We're using this new standard deviation, and that is your margin of error. So it's the T value times the standard deviation. That gives us our margin of error. Then you add it to the mean and subtract it from the mean. Questions before we do math? I'm going to highlight this. Don't forget the n-1 degrees of freedom. All right. Oh, one more thing. Notice the T is sub alpha divided by 2. Because our confidence interval is a center, we're going to cut that alpha in half again. So if we had a 95% confidence interval, we'd do 0.25 or 0.025. We'd still cut that in half. All right, let's do some math. So we're going to construct a 99% confidence interval about the population mean with this sample, our standard deviation. Whoa. Our standard deviation is 0.02 and the mean is 2.464. All right, let's do this math. So I'm going to find, I already have my mean and my standard deviation. I need to find the new standard deviation. So I'm going to put it all together. So I'm going to take my T, I need T sub alpha divided by 2 times the S divided by the square root of N. So what that's going to be, I'm going to look at my sample size is 17. So I'm going to go to my table. Wait, what's my confidence level? My confidence level is 99. So I'm going to go to my table and I'm going to get to 16. Remember, you're dividing your alpha in half. Therefore, so I do 1 minus 0.99, which equals 0.01. 0.01 divided by 2, 0.005. This is what I'm using. Okay, sorry, I keep jumping back and forth. So I'm going to go 0.005, which is right here, and go all the way down to 16. So my T value is going to be 2.921.
Where did the 16 come from?
Because it's n-1 degrees of freedom and our sample size is 17. So I subtract 1 from my sample size, and that's what I use. And it's always going to be that way when you're looking at t-values. You're always going to use one minus, or sorry, your sample size minus 1, always. So I use 16 because our sample size is 7.
Oh, okay.
Yeah. Are you good?
I didn't see the sample size in here. I don't know. It's maybe.
Well, it's just the reason I knew it was 17 is because when we found the mean earlier. So this is 2, 4, 6, 8, 10,
All the samples.
17. Yeah. When we found the mean a little while ago,
God.
it was 17. So that's why it's stuck in my brain. Sorry about that. Sorry for confusion.
Okay, okay.
Okay, we're good?
Thank you.
Okay, good. Thank you for asking. I'm sure somebody else was like, where did that number come from? Okay, so 0.005, 16, and so 2.921 is my t-value times, I've used parentheses, why not? My standard deviation, 0.02 divided by the square root of 17. So we leave the 17 there because it's n. The alpha is the area in the n. So it's like, so this is my alpha. This right here is alpha. It is the part of the curve that's not in your confidence interval. That's what alpha is. So you should be able to put this whole thing in your calculator. Let's give it a shot. So I got that my margin of error equals 0.014 approximately. That's what I got for my margin of error. Please correct me if I made a mistake, because I do that. All right. So now we need our confidence interval. So one way to write it would be 2.464 plus or minus 0.014. Oh, wait, no, I did do that. Okay. I'm like, wait, I messed up. I didn't. The other way to write it is to actually add the 0.014 and subtract the 0.014. So I'm going to put it in my parentheses. 2.478 and 2.45. 2.464 is the mean. It's up here. It's the mean. It's okay. So these are the two ways. So we can say, I am 99% confident that the actual population mean weight of pennies in grams minted after 1982 is between 2.45 and 2.478 grams. So that's what you would say. You'd say, I'm 99% sure.
Can I ask a question?
Of course.
I was trying to follow all this, and what was the 1 minus 0.99 and then the 0.01 divided by 2? Where does that go into the calculation?
This is the alpha divided by 2. Because I'm using that on my, so I am using T sub alpha divided by 2.
Mhm.
So that is, I'm going to draw the picture if I have room. So if I have a 99%, there's 0.005 in each tail.
Uh-huh.
That's where that is.
Oh, gotcha. Okay, thank you.
And I've got that dumb thing here. I wish it would go away. It used to go away, but there was like an update or something and it quit going away. All right. Any more questions? I don't want to leave you with confusion.
Are we going to do another one of these so we can do it a little bit slower? Because I got a little lost. I'm
I don't
kind of grasping, but I feel like it
what
just
else
went
I
by
got.
too fast.
Okay. Well, let me see. It looks like yes. I have another one. All right. Okay, so here's the math with it all typed out pretty. This is the math typed out pretty. So it shows you all the things that I did here. So we are 99% confident the mean weight of pennies minted after 1982 is between 2.45 and 2.478 grams. So yes, we do have another one, and I'm going to show you the fancy calculator function. So you actually don't have to do these by hand. So yeah, I mean, we like fancy calculator functions. They save a lot of time. All right. More questions on this one before I move on? Yes, we'll do the other one. I'll try to slow down a little bit more. Okay. All right. So the website fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. The data below shows the reported miles per gallon of Ford Focus automobiles for 16 different owners. We're going to take it, treating it as a simple random sample of all Ford Focus automobiles. We're going to construct a 90% confidence interval. So I need to put these values in my calculator because I need to find the mean and the standard deviation. So I need to put it in the edit screen. So I'm going to go over there right now. So I'll hit stat, edit, and I have so much stuff in my calculator. So clear, enter. Okay, I'm just going to enter these in. I'll do it slow so that you can enter them along with me if you didn't print this out. Especially since I tend to do typos in my calculator. Not bad gas mileage. Okay. Oh. All right. So I have 16 in there. Did it look correct? So I'm just going to do one variable statistics, just one bar stats. We've been doing this for a while. Hopefully this is like second nature for you now. This needs to be gone. I'm just going to write these down. I need more room on my page. It's okay. So my mean, my X bar is 36.8. And my standard deviation this is a sample. So I'm going to use 2.92. Any questions on where these numbers came from or any of that? Are we feeling okay?
Yes.
Good. Good, good, good. Hoping. I was like, that's from a couple of chapters ago. I'm hoping y'all got that. Okay. So remember, this is how we find our margin of error. T sub alpha divided by 2 times S over square root of n. This is my margin of error. Our sample size is 16. So we're going to use 15 in our table, our T table. We're going to use 15. We are constructing a 95% confidence interval. We need to use alpha divided by 2. So you do 1 minus 0.95 equals 0.05. Or use 0.05 divided by 2. So this is 0.025. This is what we are looking at the top of our T table. Hopefully you're all still with me. Okay, So the t-table, we're going to use 15 and 0.025. Pop over here. Here's the 0.2025, and here's 15. So it's right there. Did everybody see where that value is, the 2.131, and how we got that? Feeling
Yeah.
okay? Okay,
Mhm.
good. All right. So now all I'm doing is I'm going to take this formula to find the margin of error. The S is that 2.92, and the T sub alpha divided by 2 is the 2.131. So my margin of error, 2.131, I'm going to use parentheses, 2.92 divided by square root of 16. 16 is our sample size. So just put that in your calculator. All right, still with me? So my confidence interval would be this mean 36.8 plus or minus 1.56. The other way to write it would be to add 1.56 to 36.8 and subtract. So I have 35.24. I don't know why I didn't just do this in my head. That was an easy one. All right. Yes, the n minus 1 is only for the t sub alpha divided by 2, only for the t value. Good question. So it is only for the t value. Otherwise, use the n. All right. So I could say my conclusion would be I'm 95% confident that the actual average fuel economy for a Ford Focus, 2011 Ford Focus, is between 35.24 and 38.36 miles per gallon. Questions? I'm hoping all of you have the next calculator function I'm going to give you. I'm pretty sure you do. Because this calculator function is going to make your life so much easier, so much easier. So I'm going to pop back over. The nice thing is we all already have the data in our calculator. We all have the Ford Focus data right there in our L1. So if you do, I'm going to get out of there, second vars, and that's not where you're going. Ignore that. Do second mode to get out of it. Go to stat and tests. We are going to T interval. It's number 8 right here. T interval. So the nice thing is, if you have a list of data, you can use the data function right here. If they give you the mean and the standard deviation, you can pop over to stats and you can input the mean and the standard deviation. So you can either do it with a list of raw data, or you can do it with the mean and the standard deviation given to you. So nice thing here is because I already have the data right there. Click on L1 because it is in our L1. Frequency, just leave it at 1, 0.95. That's our confidence level. And this tells you what the mean is, tells you what the standard deviation is, and then it gives you your confidence interval. They don't round, so it looks a little bit different than what we had because they don't round, but it's close enough. So you would, if you wanted to find what the margin of error is, take this mean that we have right here and just subtract it from that upper value and it'll give you the margin of error because the um, you might want to write it as 36.8 plus or minus. So you would need to figure out what did I add to 36.8 to get that. So going back, I'm going to jump back to the pennies. So I'm going to show you with the other way. So going to tests and go to T interval. So I'm going to use the penny data. So it gives us that it's 2.464, and then it gave me a standard deviation 0.02. And my sample size was 17. My confidence level was 0.99. And it does the exact same thing. We had 2.45 and 2.478. These numbers fit perfectly with what we just had. So depending on if they give you the data or if they give you just some statistics, you can use the T interval. But questions about T interval? Questions about calculating the confidence interval, because we're going to jump to sample size here in a second. All right. Let's talk about sample sizes. So we did this yesterday where we worked backwards, and just as yesterday, we always round up to the next highest whole number. This is a little bit different because we have a different formula for standard deviation. So it has to look a little bit different. And we don't have the P times 1 minus P and all of that. So our problem with our sample size, using our sample size here, is that in order to have a T value, you have to have a sample size. Therefore, we're going to use z-scores when we're calculating a sample size because there's no way we can come up with a T value. It doesn't make sense. We can't come up with a T value if we don't have a sample size. So in this case, we're going to use the z-scores. And you can use your inverse norm or you can use your table. So let's actually do an example here. So we want to know how large of a sample size is required if we want to estimate the mean weight of a penny manufactured after 1982 within 0.05 grams with 99% confidence. We're assuming that the standard deviation is 0.02. My formula, as you may recall, N equals Z sub alpha divided by 2 times S divided by the margin of error. I'm going to put the M in there, squared. So 99% confidence, I'm going to go back to my other screen. It's on my table. 99% confidence is 2.575. Obviously, you can use inverse norm if you need to, but if it's one on our table, why not just use it? So I'm going to say N equals 2.575 times tried to make that extra dark so it doesn't look like a decimal, times 0.02 over within 0.005 grams squared. You should be able to put this whole thing into your calculator. And make sure you tell me if I mathed it wrong again, because sometimes, I typo. Maybe it's on my next screen. There it is. It's on the next screen. Got it right. So remember, we always round up. So I need a sample size, 107. I need to survey 107 people to have that 99% confidence. Questions? Right. And I have you do one. Okay, so I want to go back though. What was our standard deviation on that one? I'm just going to go back because I hate that it doesn't carry it along. Our standard deviation was 2.92. Okay. Okay, I would like you to calculate this. I'll get the z-score for you also. So 95% is 1.96. So calculate the sample size that you need to estimate the mean within 0.5 miles per gallon with a 95% confidence. So go ahead and math that out. I will work quietly behind you. Don't forget to square it.
Where did we get the 2.92 from?
That's the standard deviation from back here. Because this is the same data that we already used. It's our standard deviation right here. Whoops, I just erased things. See here, right here, standard deviation that we calculated in our calculator with one of our stats.
Oh, so it came from this example. Okay.
Yes. Yeah, I just went back to the previous example and grabbed the information. So I got 131.02, so the n would have to be 132. Do y'all get the same thing? How'd we do? Good? Okay, good. All right, so that's how we find the sample size. I find this much less cumbersome than the proportions, the sample sizes with the mean. To me, it's much less cumbersome. It's just quick. And I think it's just because the standard deviation formula is not quite as complex, so it's much faster. All right, so the next two slides, if you don't print out the whole slideshow, the next two slides would be the two you'd want to print out. They are kind of comparing 9.1 and 9.2. So in section 9.1, the words you're going to see, it's going to say something proportion of something. So if it has the word proportion in it, you're doing the 9.1 stuff. If it has the word mean in it, you're going to do the 9.2 stuff. And this is going to be z-scores, z sub alpha divided by 2, and this is going to be t sub alpha divided by 2. And I believe there's a handout. And then also this has I'm just gonna, why don't I just do this? P hat times 1 minus P hat divided by n, and then times s divided by square root of n. Okay, these are your margins of error. So this is the difference between the two. If it says the word proportion in it, then you're going to use z-scores and you're going to use that formula for margin of error. If it says the word mean in it, then you're going to use your t-values and that standard deviation. Okay, I'm going to pop to the next screen. So this is for the sample size. So sample sizes, it says If it says that it wants it within a certain number of percentage points, that's what you're going to look for, or within 3% or within 2% or something like that. It'll give you a percent that it wants you to be within. That's where you're going to use the p hat times 1 minus p hat times z sub alpha divided by 2 over the margin of error squared. That's for your n. And for the mean, it's going to say something like estimate mean miles per gallon. It's going to say something about estimating the mean for the, and then you're going to use that other formula. That's the ugliest writing I've done all year, all term. So this is a good comparison of the two so you can see how the problems are worded. Obviously, in your homework, they're going to be split, section 9.1 and 9.2. But once you get to the test, they're not going to be split. So you're going to want to look for those words, those like trigger words. Questions before we jump to the lab? Okay, I'm going to go to the lab. I was working in the lab. Sorry.
Is there a difference between the ME for the like margin of error and big E?
No, they're exactly the same thing, just different notation.
Okay, perfect.
Yeah. Oh, sorry. I just saw that you typed it in the chat. Yeah, the ME and the E are exactly the same thing. It's just different notation. So I'm hoping,
Okay, thank you.
you're welcome. I'm hoping this is the lab. I'm hoping that everybody still has their data analysis stuff turned on in their Excel. I mean, I think it's kind of more of a pain to turn it off than to just leave it, because we're going to use that descriptive statistics tool again, the one that we used for, is it lab 2? Is that what lab it was? I think so, lab 2. So it's the same tool. We're using that tool again. And you're going to use your continuous data. You only need 20 data values, even though I think the instructions say 50. You only need 20 data values. You're more than welcome to, if you want, since you have it. You could always grab one variable from your final project if you chose to, or you can just use the continuous from your previous labs. I don't care. I don't care what data you use. Just grab some data. So what we're going to be doing today is we're going to be creating a confidence interval, and we're going to be talking about what that means. So I'm going to go ahead and go to data right here. And that's not data, that says draw. And I want to do my data analysis. Okay, got it. Do the data analysis, which we've been here before. And then once again, go to my descriptive statistics. This is the same thing we were doing before. You go to data, data analysis, descriptive statistics, and then click OK. The input range is all of my data. And I have a ton of it because I did like 100 something countries or something. Okay. Now my output range is going to be in this box right here. Now there's a couple of things that we need to check. Once again, I'm going to check on click on summary statistics, but now we also want confidence level for mean. I don't care what confidence level you use. It defaults to 95%. Feel free to use 90, 99% or 90% or whatever you want, or just leave it. It defaults to 95. Don't forget to check that box. I'm going to click OK, and it's going to put it in here. Okay. As with the previous lab using descriptive statistics, I want you to use Excel tools to put things where they go. So margin of error is where it says confidence level. I'm going to move this a little bit more. Where it says confidence level, this is your margin of error. So I'm going to click on equal, click on that, and hit enter. The mean is right here. So I'm going to click on equal, my mean. To find your lower bound, you're going to take your mean and you're going to subtract the margin of error. So I'm going to do equal. There's the mean minus the margin of error. Enter, and it's going to give me that lower bound. The upper bound, hit equal. I want the mean plus the margin of error. Hit enter. So now I have my confidence interval. I have my lower bound and my upper bound. Hannah, it looks like you're about ready to ask a question. Are you good? Okay. So now in the interpreting the results, I want everything to be in the context of your data. My data is magnitude of earthquakes. So in number 1 here, I am estimating the population mean magnitude of earthquakes. That's all I would say there. I'm estimating the population mean magnitude of earthquakes. If you were estimating miles per gallon in Ford Focus cars, you would say, I'm estimating the average miles per gallon of Ford Focus. The population mean. I would like the word population in there. You are estimating a population mean, whatever your data is. In the context of your problem means you need to reference what your data stands for, what it is. Don't just say, I'm estimating the population mean. You have to tell me, reference what your data is. Mine is magnitude of earthquakes, could be miles per gallon, could be temperature, whatever it is, you are estimating the average population mean. How confident are you? If all you say is, I am 95% confident that the average magnitude of earthquakes is in my interval. You're not actually doing your final thing yet. This is basically scaffolding it. So I'm 95% confident. The interpreting your confidence interval, this is where you put everything together. So I would say I am 95% confident that the average magnitude of earthquake is between 6.86 and 7.23 on the Richter scale. There you go. You're going to actually state your findings based on what you have. All right, that's it. Questions? Oh, that was easy. Nobody's asking me questions. This one's pretty straightforward and fast. Go ahead.
Sorry, Melissa.
Yeah,
This is your Tuesday, correct? Just double checking.
I believe so. Let me pop over to my open math real quick. Let me pop on over. Yeah, it's due Tuesday.
Okay, thank you.
I almost always make the labs do the day after the homework. I just wanted to make sure. Yeah, it's due Tuesday. And I mean, if you have your data already, this will take you all of 5 minutes. It's an easy 10 points. Anybody else? All right, so this is all I have for you. Any questions that should be asked on the recording so other people can gain the knowledge as well? Any recording questions? Okay, I'm going to stop the recording.